Tellus. So chi-square goodness of fit is what we're going to be looking at today, and we're dealing with Skittles. Now, we've done a number of tests up to this point. We've done tests where we standardize for an individual, where we standardize for a group, where we standardize for a proportion, where we standardize for two proportions or two groups. But what if we have more than two groups, right? Because like here in our example, we have 5 groups, 5 colors, right? So what do we do then? Well, that becomes a chi-square test. And it's a little different. It's still a test, meaning that we're looking for significance. But let's just simply start with our hypothesis, our hypotheses. In this case, the null hypothesis isn't going to be something like P equals or M mu equals or something. It's a little bit more of a statement. What would we expect in terms of our numbers of colors to be? Even, right. We should expect them to all be the same, right? So our null hypothesis would be we have equal numbers of all colors. That's what we expect if we don't know anything else.
But what we expect more of a randomized? I don't know what they would be.
So,
I mean, I don't mean to, because I totally agree.
If you flip a coin 10 times, what do you expect? Right. Okay. That's what we expect. Does that mean that that's what you're always going to get? No. Right. And that's where probability comes into play. Yeah? Okay. So the null is what we expect. The alternative is a little different than we've looked at before. It's at least one color is different. Not in terms of value of the color, but how many we get. And that's what the chi-squared test will tell us. It's pronounced chi. Yeah. It should be chi latte, shouldn't it? According to this lesson. E is expected number of I'm going to use orange as an example because that's my favorite. Use whatever color you want. In this case, calculating the expected value, because we've said that we expect them all to be the same, is simply going to be the total n divided by 5, because there's 5 colors. And we use E as this value. But what if I said that you're going to get twice as many reds as greens? Then that changes things. So for instance, we did this with M&Ms. M&Ms has a very specific distribution of values. So there's more of one color than another. So let's say 40% of the Skittles were orange, then you would do 0.4 times your n value, and then whatever times each of the other colors. So this is not an every time, it's just because of our hypothesis being that they're all the same. And this can be a decimal. E can be a decimal. Okay.
So is that a 5 or
Yeah, it's a 5. Because there's 5 colors. All right. Now, we have the expected, what we expect. The next thing is what have we observed? That's O. That's the actual count of a particular color. observed cannot be a decimal. So if you got half of a green, you either say you got nothing or you got one whole, right? There's no halves. So no decimals here. Your observed cannot be decimals. The calculator will tell you to go jump in the lake if you put a decimal in there. So the calculation works like this. It's the sum of the observed minus the expected quantity squared over the expected. So for each color, we would do this and we would add them up. It's a fairly simple formula. Alright, so here's what I'm going to do. I'm going to put down my values. I think you should put your values down. So I had, my n value was 46. I got a pretty full thing. Most of them have been around 40. And I had, let's see, reds I had 9. Green. And use your own numbers. So mine were 9, 12, 7, 13, 5. And so my calculation is going to look like this. For my reds, that's going to be 9. Oh, wait a minute. Back up. What's my expected? So we need an expected. It's 9.2. So I expect 9.2 of each color or flavor. So for my red, that's going to be 9 minus 9.2, quantity squared over 9.2, plus my green, 12 minus 9.2, quantity squared over 9.2, plus my purple, 7 minus 9.2, squared over 9.2, 13 minus 9.2, and what this is going to give me is my chi-squared value. So I'm just going to go into the calculator and make this work. You could do this with fractions, or I just do like this. You're whining now? How long have you been in this class? Well, that's the senior. That's the senior in you. Yeah, you square it and then you divide that by the expected. I'm hoping that you're putting in different values for your own, right? So once I've put all that in, assuming that I have everything correct, that should give me a chi-squared value. About 4.87, I guess. .9 would be fine, probably. So the chi-squared value is like, it's like t or z. It's what you take to the table. But we need degrees of freedom. Degrees of freedom in this case are easy. It's just the number of groups minus 1. So in this case, degrees of freedom would be 4. And if I could get everybody to look up here real quick so I can show you this table and how it works. It's pretty straightforward. Let's see, I'm looking for 4.87. My degrees of freedom are 4. But I'm not on the table. So what that means is my probability is greater than 0.25. Because my 4.87 is less than 5.39, and these numbers just grow, right? That makes sense? So my probability is greater than 0.25. It's also, that would also be greater than 0.25. Yeah. What's that? It's the number of groups minus 1. So you've got 5 colors minus 1. Yeah. Okay, now, looking at this, here's something you might consider. Anything this side of the 10% is going to be a fail to reject. This is not significant under any circumstances. Right? This is going to be a fail to reject the null under any circumstances. Not significant. Not sign. Not significant. But conversely, any probability that we have that's less than 1% is going to be significant, right? Under any of the conditions that we have set forth in this class. Now, if you set an alpha at 5%, then the 10% is not significant as well, right? But anything on the yellow side is going to be fail to reject under any alpha. Anything on the pink side is going to be reject at any alpha.
So when you get that value and you put it into that calculation, what did you get?
What did I get?
Yeah, what did you get?
I got 4.87.
And then you put that value on it here?
Yeah, so what I did is I looked at 4, because that's my degrees of freedom,
Yeah.
and I looked across until I could find 4.87. Well, I can't, right? So the p-value has to be greater than 0.25. So if you look above from the 5.39, which is the smallest value, my p-value has to be greater than 0.25. Okay? Now, your p-value could be different. I'm hoping that somebody has something that's significant. I'm not significant with my sample. So my p-value,
There's got to be like a test for this.
you think?
Probably.
Yeah.
Wait, so I got 8.24, would that be?
Okay, well let's have a look at 8.24. So I'm going to go to 4. 8.24 is going to be between 10% and 5%. So at that point it becomes, what are we talking about? what would your alpha be, Sydney? We're talking Skittles here. You 0.5 for Skittles?
No, that was. Wait, what?
I would do 10%.
Sorry,
I'm giving you
way too much.
I'm giving you a hard time. I would, in your case, I would say that you are significant. You have a significant difference in at least one color. Okay? Yeah. Because we're talking Skittle colors here. It's not all that serious. You're not going to be sued, and it's not life or death. So I think 10% is a reasonable alpha. So if your value's less than 7.78, I'm sorry, greater than 7.78, which makes your p-value less, then yeah, you'd be significant. Okay? Yeah. All right. I didn't need to set a p-value or an alpha because my p-value is junk. Okay, so how should we answer this? Okay, chill out. Chill out. So, in my case, I fail, or we fail to reject the null. We fail to reject the null and conclude there is not a significant difference in the color distribution of Skittles.
So what happens if it's in the gray area, like in between significant and not significant?
Well, then it depends on what alpha you set for it as to whether you decide if it's significant or not.
Okay.
So if you set alpha at 1% or 5% or 10%, then you have to decide is your p-value significant, right? Not, what did I say? There's not a significant difference in the color distribution of Skittles. That was because my p-value was far greater than any reasonable alpha. But Sydney should answer differently. Sydney should reject the null because the null should probably be set at 10% in this case. She's going to say we reject the null and conclude there is a significant difference in at least one color of Skittles.
Yeah, so what about other groups where the degrees of freedom are more than that? I'm just wondering, because for the degrees of freedom, it's...
I wouldn't worry about it. I don't think they're going to run across anything that large. It probably goes to Z. It's my guess. It's a fair question because it doesn't say, does it? I would round it down to 100. If you have 1,000, make it 100. If you have 10,000, make it 100. That's what I would do. Okay, good question though. So this would be if your p-value was less than 10% in this case. And the calculator, here's what I want you to do. Take your calculator. There have been a couple that have given us some trouble, so if it gives you some trouble, let me know and I'll set it aside and try to figure out what's going on. Let's go to your lists. So in your L1, I want you to put your observed values. What did you observe? Let's see, what did I observe? That was 9 and 12 and 7,
Then you're 7 months.
13 and 5. Yeah, and in your L2, you put your expected. Now, it's going to be the same number for each one. Mine was 9.2, but yours is maybe going to be different.
So what's in L1?
L1 is just how many did you count for each color? That's your observed. L2 is your expected. Once you get that in there, then we go to our test, which Peyton said he found something.
Yeah, is it the x squared test or whatever?
Chi-squared goodness of fit, yes. So if you go over to tests, the goodness of fit test or the chi-squared tests are kind of at the bottom, so I like to go up to get to them. We want D, chi-squared goodness of fit. Chi-squared. So observed was the L1 in my case, probably yours too. Expected was L2. Degrees of freedom in this case is 4. 5 colors minus 1 is 4. We calculate that. And hopefully I get the same chi-square value that I calculated longhand. I did, 4.87. And my p-value, I said it was greater than 25%. It's 30%. And each one of these values in this CNTRB, I'm not entirely sure what that means, I just know what it is. These are the individual chi-squared values for each of these calculations. So for example, if I just did this, that would be the 0.00434. If I just did this one, that one would be the 0.8521. Okay. So I think if I were doing this for an AP test question, I would probably include those guys. I'd round them maybe at 4 decimals, 4 or 5 decimals, but I would include those values as well. Okay. As far as I'm concerned, I'm not that interested in it unless you're going to take the AP test. All right, so let's talk about what this p-value and stuff means. Not only is my p-value greater than a reasonable alpha of 10%, what that p-value means, in my case 30%, is that about 30% of the time I would expect a distribution like what I observed. You can get very high p-values here, and that's okay. Like last class we had somebody who had 96.96, which means that they had almost a perfect distribution, almost the same number of each of the colors. So it's only when we get a value that's less than 10% or less than 5 or less than 1, if you set those limits, are you concerned about it being significant. So chi-square goodness of fit. The goodness of fit only works when you have 2 columns. What if you have 3 or 4 or 5 or 100 columns? Then that's the straight up chi-square test. So we'll get to that in the next couple of days. All right. The other thing chi-square doesn't do is it doesn't tell you which one is abnormal, either too small or too big. It just says, yeah, one of them's out of whack. Doesn't give you any indication as to which one. So.